Okay, so equilibrium safety spending by everyone is C bar over EN. Or because S can only go up to 1, it'll max out at 1 if C bar is bigger than. All right, so we've got 3 kind of variables to look at the comparative statics for. And I think the impacts are sort of intuitive, but not always for intuitive reasons. So having more firms lowers equilibrium probability, equilibrium safety spending. And this raises risk overall, but not directly due to the fact that there are more firms that are all doing risky things, posing risk, but purely because all the risk comes from the winner. If you're a loser, you can't pose risk. The probability that everyone survives is the S chosen by the winner, which is the equilibrium S. But the S chosen by the winner is lower when there's more N. And the reason for that isn't that when there are more players, each person has a greater, is sacrificing more of a chance of winning if they spend a bit more on safety, right? The sacrifice, as we saw, is just 1 over C bar, which is independent of that. Okay? The only reason why when you are facing lots of competitors, you don't want to spend as much on safety is just that it lowers the benefit of spending on safety, because the only benefit you get from spending on safety is if you win, and you're less likely to win. So that's the channel through which more competitors is lowering equilibrium risk here. Yeah. More enmity means lower spending on safety. Hopefully that's intuitive. It just sort of raises the payoff to winning. And higher C bar raises equilibrium safety. And the way to think about that is that the safety range is fixed at 1 unit. The range of possible amounts that you can spend on safety. But the capabilities range is growing with C bar. And so high C bar means that in some sense, the distribution of C minus S, which is what governs who wins, is mostly determined by this random thing, which was the capabilities. So you can sort of afford to be safe. If C bar is infinity, then you can set S equal to 1, you got all the benefits of safety, and you have that has no impact on the probability that you win. If you were higher than your competitor before, you're going to almost certainly be higher than your competitor after. I think for time, I won't currently try to draw an analogy between some of these comparative statics and the risk compensation stuff we did before, but hopefully it's simple enough that you can kind of think about it on your own time. And you can think about the relationship between enmity and K, for instance, right? K being, payoff if you just don't kind of jump in the race and try to develop capability. How much you like life without competing on AI. Yeah, I mean, so Zach will talk more about governance explicitly, but off the bat, to the extent you believe this model, there are some governance implications that come to mind. So you might want fewer competitors, right? You might also want to induce less effective enmity via some sort of redistribution from the winner. This is one of the motivations for that windfall clause that Cullen O'Keefe and co-authors came up with a few years ago. The hope is that by getting companies to commit in advance to redistributing some of the outsized gains they get, if it turns out that the winner of an AI race gets that permanent monopoly over everything or something like that, that's good for equality reasons maybe, but it could also be good because each player doesn't care that much about whether they win. So in a sense, you're lowering the enmity there. Okay. Obviously, by the same token, on both counts, by the same token, it can be bad if you don't care about safety and you just want to speed development as much as possible. Okay, any questions about the no information case? All right. Now suppose each player observes their own capabilities, but not those of others, before they choose how much to spend on safety. Technically, the strategy set now is not an S, but a set of functions from observed own capabilities to safety levels. And we'll assume that it's differentiable. People choose a differentiable function. We'll still solve for the symmetric equilibrium of those differentiable functions, and we'll assume that that symmetric equilibrium has the property that whoever is highest C always wins. So, maybe they spend more on safety if they observe they have higher capabilities, but not by so much that higher C means lower C minus S of C. Because the winner is whoever has the highest C minus S of C. And if it were the case that you wanted to spend so much on safety that you actually were more likely to lose if you had higher capabilities, then if you had those higher capabilities, you would wish that you hadn't. And you would kind of, presumably, there's like some sort of free disposal for capabilities or something. Okay, so what's the probability that I wins given their capabilities and given the equilibrium function? Well, because of this condition, it's got to just be the probability that all n minus 1 other players had lower capabilities. Can you see that? So it'll just be like, yeah, CI minus CI is this, level, this divided by C bar is the probability that any given other player has lower capabilities. And that to the n minus 1 is the probability that all of them do. Now, to figure out what that equilibrium function is, think of it this way. Suppose that I choose some alternative function such that around some particular level CI, you spend marginally less on safety than the equilibrium S star would recommend. Then your probability of winning at that CI relative to the equilibrium has to rise sort of per unit that you've deviated, per unit that you've skimped on safety at CI, by how much higher a level of capabilities would yield the level of competitiveness that you're kind of buying for yourself by scrimping on safety. Okay, so how much higher would C have to be such that if I were playing an equilibrium, my C minus S of C would be what it actually is, given that my C is actually a bit lower, but I'm raising my C minus S by lowering my S as well. Okay, so that's how much more capabilities I'm playing as if I had by scrimping on safety. And then this is just the increased probability of winning per unit of increased capabilities. This is going to be my impact on probability of winning. You can see this sort of visually by plotting that C minus S of C function. So this is C, this is C minus S star of C. We're assuming that this is increasing, or weekly increasing. And we're saying we've got this uniform distribution from 0 to C bar of from which the actual capabilities are drawn. And if I'm here, actually, but I don't choose S star of C, I choose lower S. The question is, how much to the left am I moving here? Given that I lower, if I lower S by a unit, or let's put it the other way. Let's say I raise S by a unit, so I lower C minus S by this, right? How much I'm moving here, I'm acting like I have lower capabilities, that's going to be 1 over that's going to be the slope. That's the question in reverse. The denominator there on the left is the slope of this line, right? That's the derivative of C minus S of C around this particular CI we're interested in. The derivative of that with respect to C. Right? But we're asking, what's the impact on this of changing S a little bit? So it's just going to be the inverse. And we're going to multiply that by the derivative of your chance of winning in C. So we just differentiate that thing there. And that's the formula. So that's, yeah. That's got to be how around S star, if you kind of change S a little bit, what happens to your probability? Your probability winning has to satisfy that formula. And then you can multiply this by your marginal increase in expected utility from winning at CI above that baseline. This is still the formula for your expected utility overall. Your marginal loss of expected utility via winning at a lower safety level. Oh, yeah. So, right, so this is the trade-off. So you increase your chance of winning by a bit. But what do you get if you win? You don't get 1 unit of payoff. Like you get S of CI. This is the payoff you get. Because like if you win, but you blow up the world, that doesn't count. So you only get S units of payoff. And then you've got to subtract what you would have gotten if you hadn't won, because like the person in this interval won instead. Okay. Which is 1 minus E times the that same S star of CI, because we're around CI here, right? So you're just displacing someone who would have chosen a similar safety. And that difference is S star of CI times E. So that's the payoff that you get. So you're increasing your chance of getting that. And your loss in expected utility via winning at a lower safety level, because given that you win, we're differentiating with, we're saying, what if you're scrimping on safety a bit? That's just the probability that you win at all. This is his general point that like the only benefit of safety is, comes if you win, and then we've got like some expected benefit because you're less likely to die, given that you're safer. Well, by the same token, the only cost is that if you win, you're losing like 1 unit of utility per unit of foregone safety. Okay, so this is the benefit, the marginal benefit. This is the impact on winning we saw from the previous slide. This is the extra utility you get from winning around that margin, and this is the cost. And the two have to be equal. And rearranging them, you can get a differential equation which has S prime as a function of S. And solving it, you get a closed form expression for the equilibrium safety as a function of CI.
The argument for why C minus star is increasing in free disposal, is that meant to like follow from free disposal instead? I could imagine that if you get sufficiently high C, then you're going to have a lower chance of survival. A lower chance of winning,
sorry. So to answer the first question, it's not that it like in the paper they don't assume some sort of free disposal and then say from that we can infer that C minus S of C is rising. They just say we'll solve for the unique. It turns out we can find a unique equilibrium that is symmetric and satisfies this condition. And a reason why we think that this is a reasonable equilibrium to suppose. Maybe there are others. They don't rule out that there are other, but they think it's reasonable because of the free disposal argument, that like any other equilibrium, if we expanded the game to allow for disposal of capabilities, people would want to take advantage of it. Does that answer your question or no? Okay. Okay. So from here, you can work out the equilibrium probability of survival, and that'll just be integrating over all the C's from 0 to C bar of the probability that the winner is at that C times the probability of survival given that the winner was at that C, which will just be, I should have had a star there, which will be S star of C. Does that make sense? Probability of survival in each case, the probability that that case obtains. So, I mean, probably not worth it, but you can get, you get how you would do it, right? You integrate from 0 to C bar of probability density times S star of C. And you're going to get these two cases depending on what C bar is. And this is kind of for the same reason as we had a kink before. If C bar is low enough, then remember, C bar is high, people want to spend more on safety because we're all more spread out if C bar is high. So there's little cost to spending on safety. And we're going to be in this sort of corner solution where at least some people want to spend 1 on safety rather than something interior. Whereas the C bar is low enough relative to N. Everyone's in the interior solution, you know, spending something between 0 and 1 on safety. No one wants to spend nothing on safety because that would mean that, like, if they win, they get 0 payoff because they die for sure, right? So you don't have to worry about that second kink. Okay. Now, we have these 3 comparative statics, right? The N, the E, and the C bar. And without working through it, it turns out that raising the number of competitors now has an ambiguous effect on the probability of survival. Who can intuit why that might be? Well, so what governs the probability of survival? Like, what's the variable that'll always equal the probability of survival? It's safety investment by like one person. Which person? The winner. Right, right. Now, in the no information case, the winner was equally likely to spend, everyone spends the same amount on safety, and the fact that the winner had higher capabilities, that had no impact, no relation. There's no channel by which that could affect how much they spent on safety. But here, the benefits of spending on safety only accrue if you win. And so if you're less likely to win, if you're behind, then you're going to spend less on safety. Okay? Which is like, maybe that's kind of intuitive. If you're really far behind, you're going to spend less on safety. It's just a long shot that you'll win anyway. You can't afford to give up more of that by spending on safety. And you just don't get much of a benefit because you're probably not going to win anyway. So the only way that we end up with a winner who spends very little on safety is if by some fluke, someone who got a low draw of C, and so they thought that they were really far behind, actually was at the head of the pack because everyone else was even further behind. And that's going to get less and less likely the higher N is. Okay? So when there's more competitors, it can turn out, it could go either way, right? But it can turn out that with more competitors, it's just more likely that the winner was actually someone who correctly understood that they were probably going to win because they had high C and they invested more in safety. The other two effects are the same. More enmity means people are more keen on winning rather than winning safely. lower equilibrium probability of survival. And then higher C bar, as I was saying, when people are more spread out, they understand that they can each afford to spend more on safety, and there's more equilibrium safety. Okay. We can also do comparative statics on the probability of survival, just full stop. And there are these two cases, but it turns out private information just unambiguously makes things worse. It makes the case where we're on the wrong side of the kink more likely, where like people aren't maxing out and setting us into one, or the winner isn't, I should say. And it increases risk in each of the two cases. Do you have any intuitions on why this might be? Giving people information about their own capabilities makes equilibrium riskier. So, should I come in one at a time? The cost of lowering your own investment in safety is just that you might do damage if you win. And if everyone's ignorant, then they're thinking, oh, there's like a 1 in n chance that I'm going to win, and so maybe 1 in n, that's still a pretty high chance, and so I don't want to cut back on safety too much. And yeah, and importantly, like the fact that you're skimping is going to like be a lot of evidence for you that what's the idea? So spending less on safety is going to inform you less that you're probably going to lose if you know your capabilities. So if you know that like you've got a really, really high draw of C, yeah, you can spend less on safety. Less of an update than I will win when I knows. Huh.
Winners first. The higher you are, the more likely you are to bid, but actually that makes you invest more in safety, which makes you bid less likely. So it's like you having a higher draw makes you less likely to win. That opposite effects are.
I think it's just that when you know C, you can make a smaller update because you already got some information about how likely you are to win. Whilst before, you have no information at all.
Yeah, but that would seem, now that I'm thinking about it, this made sense to me when I made this slide like weeks ago. But now that I'm thinking about it, it seems like it should go the other way. Because the thought is if you already basically know if you're going to win, then you might as well be safe. You might as well spend a lot on safety because that's not going to like tell you, oh, I'm probably going to lose now. It turns out it goes the other way. Well, I don't want, so here's a surprising fact. More information means lower equilibrium. Huh, I'm really sorry. That's like one of the most interesting results in the paper, and I'm just totally blowing what the intuition is here. In any event, thankfully, as we'll see at the very end when talking about an extension, this conclusion really relies heavily on the point that the losers pose no damage, right? And there's this people skeptical of there being a problem with AI safety will sometimes use this line, which I think has some truth to it, which is, on some level, safety is the problem of getting the robot to do what you want, and capabilities is also the problem of getting the robot to do what you want. So like, as we just kind of aim for capability, safety will come in the package. What that, to the extent that there's kind of truth in this line of thinking, sort of suggests that it's not the winner that poses all the risk, it's the loser that poses all the risk, because they're kind of toying around with the model and they don't quite know what they're doing, and they accidentally produce something which is defective somehow, and it doesn't have the capabilities of the frontier model, but it's just, one thing it's unable to do is like follow your instructions properly, and then it gets out of hand. And once you allow losers to cause damage, then more information can be given. Again, I'm really sorry. But moving on to the full information case, here it's going to look kind of familiar maybe to anyone who's thought about auctions. So we'll assume that there's this tie-breaking rule where if two players have the same C minus S, the person with the higher capabilities wins. Now let big I denote the lab with the highest capabilities, and J denote the second highest, and delta denote that difference. In equilibrium, so everyone can see everyone else's capabilities. The person with the highest capabilities is always going to win. They're always going to sort of, outbid everyone else, as it were. But equilibrium safety that they choose is going to be determined by that delta. So it's kind of like a second price auction. They've got to like just outbid the person with the second highest capabilities. More concretely, given that I chooses the SI, J can win by choosing some level of safety that's less than SI minus the capabilities gap, right? Because then CJ minus SJ will be higher than SI minus CI minus SI. And that'll be feasible precisely if SI is bigger than that delta in capabilities, right? If I lowers herself down to a level that's like so low that J, by spending nothing on capabilities, would win, then there's that gap where J can win and sort of have like a positive chance of survival by choosing a safety level in between SI minus delta and CI minus delta and CJ. Yeah.
So isn't that the private info case? It's a full info case as if you have the Myers and Kyle types, which is like your own capability adjusted for the inverse Mills ratio, which gives you a lower capability than you actually have. So your virtual type is actually less capability than you have. So in the game, you play the private information game as if you're playing a full information with less capabilities. If everybody thinks they have less capabilities, the investment into safety is less than the equilibrium. As a result, everybody invests less in the safety. But I guess again, first to comment later.
Yeah, I have no idea. Does anyone follow that? No one followed that?
Yeah.
Oh, sorry. Okay. Can you write that down? Can you post that in the Slack and we can come back to it? Okay. It could be a great intuition. J's payoff will be SJ for sure, right? Because like there's no randomness now. J knows that J is going to win by choosing SJ low enough that their C minus S is highest. That's got to be better than what they can get by just letting I win and getting this payoff, right? So it'd be desirable and feasible if that SI minus delta, which is like the maximum like gain they can get for themselves, is higher than what they can get by just letting I win. And just rearranging, that'll happen precisely if SI is greater than the gap minus the gap divided by the enmity. So in equilibrium, I is going to choose a safety level that's just enough to make J like indifferent to jumping in the race. or just going to max out at 1 if 1 is enough. Yeah, you can't choose safety more than 1. Okay. So just to like explain why if this is less than 1, so I is choosing a safety level of delta over E. The reason why I is not like, oh, well, I'm just definitely going to win, so I might as well be safer. And the reason is if they did that, then basically J would win, because J in equilibrium, in order to maintain it as the case that I actually wants to spend this much on safety, like only this much on safety, J is knowing that J is going to lose because of the tie-breaking rule. J is spending so little on safety that J would win if I cut back on safety. Okay, so J could just win for sure if J just like scrimped a tiny bit more, but J's indifferent between winning and losing and would prefer to lose at lower safety. Okay. So here, the equilibrium probability of survival is really simple. It's just the safety investment of the winner. Increasing the gap increases that safety investment, so it increases the probability of survival. Pretty intuitive. Leader has a bigger buffer. So an expectation, more players means lower probability of survival for the same old reason. You're just kind of crowding people together, so the gaps are smaller. And we don't have that counterbalancing effect of the private intro case, where like you really want to lower the chance some low type accidentally wins but invested little in safety. That's not going to happen here ever, so we just retain the standard intuition that more players means lower safety because of like the smaller gap. And likewise, higher C bar means higher gaps, so more safety. And for all the usual reasons, more enmity means you know, J needs to be discouraged more from jumping in, and you get lower equilibrium safety from the winner. You can work out the probability of survival by integrating across the cases. And you find that public information comes with lower safety than no information, just like private information. But the comparison between private and full information is ambiguous. So the only robust thing is that no information is best. Okay, here at least I wrote out the intuition, something that's hopefully more legible. Why is public information bad? As in the private information case, public information reduces the cost to the second place person of lowering how much they spend on safety. Risk has to drive her to indifference. Yeah, I guess maybe this is simpler. So for all parameters, you have some chance of getting a really small delta draw, and if you get that unlucky draw, then you have low equilibrium safety, whereas that'll never happen in the no information case. Everyone sort of got the same kind of expected gap. As I was saying, private versus public information is ambiguous. And an interesting thought they point out is that, like, okay, given the importance of these gaps, given public information, you might think that collaboration always like increases the probability of survival because you have fewer players. Like if you just kind of tie some groups of people together. And that's true, but you got to be careful, just even though this is outside of the game, because if it unravels, you'll suddenly have a bunch of players that are really neck and neck. So they're thinking maybe, yeah, if we're going to engage in some like international collaboration or something, we should better be sure it's private. Okay. Again, very briefly, there's like a literature of further tech race models sort of building on this. Stafford et al. Give each firm a continuous trade-off between safety and capabilities. And so you could kind of think of it as a bridge between Wednesday's pure risk compensation case and this case where it's just a tech race. Now, the interesting thing is that tightening the race by like pulling up the laggard no longer unambiguously lowers equilibrium safety, because now the laggard actually has more to lose, because like the laggard actually wants to invest more in safety, because it's not like, well, I'm going to lose anyway, so I might as well not invest in safety. Like they can still blow up the world even if they're the laggard. So given that they have more capabilities, like they like the world better when they're doing better, that effect can make it the case that improving how well the laggard's doing kind of increases how much they spend on safety and lowers equilibrium risk. Okay, then you've got this paper on what happens if we just like increase the price of compute. As a sort of benchmark, recall the like pure risk compensation case. Here it's kind of like NASCAR. It's like what happens if we change the price of, you know, like helmets or something. In units of utility, that C, that like capability, it's just going to depend on like how reckless you are relative to other people. And so you have this sort of treadmill where you're kind of making safety cheaper for everyone, but they're all just going to like compensate for that, and you have no impact. You can have an impact one way or the other if safety work sort of scales with compute more or less quickly than capability. But it's going to depend on that functional form. Yeah. Yeah.
You can imagine Delta's fairly positively correlated with E here, where if the main example or the main proposals for increasing Delta today, right, is prevent the export of chips to China, which I think makes the Chinese think that the Americans are trying to keep them down, and if in some like way increase the enmity between the two countries, it's easily go together.
Yeah, but I think, okay, so right, delta is the difference in just like capabilities like drawn from 0 to C bar. I think maybe what could be helpful would be to say, well, let's say we've got the game as it exists before we intervene, and so like enmity is exogenous here, and we're going to ask, yeah, what do we want to change given the level of enmity we have and like given the draws that we got? And then we can try to like increase delta. So I mean, yeah, I think we can do that. Is that fair? Am I missing something?
I think the main thing I'm saying is, I think the main way that we are trying to increase delta also has the effect of increasing E.
Oh, of increasing E.
Yeah, increase.
I see what you're saying. Sorry, I misunderstood. Okay, so where there's a feedback loop between delta and E, I don't know what happened there. Hey, sorry.
But think about how things might change if the cost of increasing safety capabilities, because like you might think that it's much harder to align like GPT-7 than GPT-4, and I definitely feel like maybe right now to the point that like if you're the leader of capabilities and have this like buffer to safety, but
No, yeah, that's a great point. I haven't done any of this work myself, right? So I just sort of, as you can tell, I'm just sort of doing my best to present what's been done. And there are a few other papers besides these. It's possible that one of those deals with that, but I'm pretty sure these don't. But they're all quite long and they have their appendices, and maybe one of them does. So I would hunt through the literature.
Risks are going to scale with capabilities, but there's no like the safety work is less. It's smaller than it's just.
Okay. Yeah, no, because that does seem very relevant, and it's not in any of these models, I'm pretty sure. Certainly not in Racing to the Press. Okay. Anyway, this is another model in which losers can pose risk. Just in general, throughout the scenarios in this model, the equilibrium probability of survival is a lot lower. And it's precisely because we have this kind of big force in favor of safety I talked about mainly in the private info case, where you're saved by the fact that only the winner poses risk, and the winner was disproportionately the person who got a high seed draw and so chose to feel like they could get away with best and lot in safety. That's not going to happen here. But anyway, there's this web tool some people have put together that combines some of these models, and you can play around with what happens at equilibrium as you change this variable or that under this assumption or that. Very briefly, I mean, on talking to the authors of some of these papers, they say that further work of this kind doesn't seem as valuable as they used to think, either in absolute terms or relative to much more applied work, like who are the actual other actors in this race here and what do they think? A general issue with getting value out of these models seems to be that the games are very super modular, meaning that one person's best response, if I invest less in safety, your best response is to invest less as well, and so on. And that means that very slight changes in assumptions can radically change sort of what everyone's equilibrium investment in safety is all at once, if that kind of makes sense. And so kind of saying anything robust about equilibrium safety turns out to be kind of difficult. So again, not really my field, but it's what they seem to think. Yeah.
What do you think of criticism that that's probably one-shot game? And so maybe thinking about equilibrium behavior here is also not the best way to
I mean, okay, a one-shot equilibrium is a one-shot game, you have less reason to think people will play in equilibrium than, I'll just leave that. Then in a repeated interaction, maybe, because you have less time to find your way to a Nash equilibrium. Is that the idea?
Yeah.
Yeah. I don't know. I mean, I feel like
world is dynamic.
No, I said it's simply like a one-shot game. We play this game once, we die, or we don't get to play it again. So.
Oh yeah. So you're saying in reality it's a one-shot game?
Yeah.
As it is in the model, but you're saying in reality we shouldn't expect Nash equilibrium behavior in a one-shot game.
Oh, maybe. I mean, that's a quick. You often get with these kind of models, right? And I'm trying to think whether one response would be, oh, but it's so high stakes, so I can think extra hard, and it's all big labs, and so maybe they're quite rational. But I don't know.
Yeah, I don't know. It's a good question. I mean, there's two forces, right? In a dynamic setting, also there's this explosion of equilibria, right? The folk theorem tells us, you get all these equilibria. So maybe you're kind of less likely to play in the simple Nash equilibrium. But also people can, even if it's a one-shot game, we might be able to communicate before we play it, in which case we can coordinate on the equilibrium. It's not totally one shot, out of the blue suddenly.
Yeah.
Have you ever thought about being what if we tried to answer the same question but with perfect competition? No strategic behavior.
No, I have not.
Going immediately to what you just said, that people build models of partially enforced safety or a partial subsidy.
Well, I think it's generally the idea is that just subsidizing safety itself, if you can do it, will generally make things safer. Even in the risk compensation case, if you can actually just subsidize safety rather than spending on it and then letting them respond, you just subsidize one thing. You subsidize potatoes or carrots, people are probably going to buy more of the subsidized thing. And so the interesting thing that Jensen and all look into is what if you can't subsidize or tax safety directly? You can only do it via compute as a whole. And the question is, under what conditions is that on balance acting like a tax on safety versus a tax on capability?
Yes, I think what I'm thinking is when you can only target some of the agents.
Some of what?
Of the agents of the players.
Oh.
So if the games are very so
super modular, like if you can regulate just one player and increase their safety, just everyone.
I see. Yeah. So that is what the prediction would be of a super modular game. Like if we're racing, and it's kind of intuitive, I think, right? Like if we're racing and you can just get one person to be safer, then you're gonna like increase the gap for any like given amount of safety the other person's investing in it. Yeah. I mean, it might depend on the details, like, if you can regulate the leader but not the follower, then you can like shrink the gap and that might make things worse or something. But on the whole, yeah, when you've got a super modular game, then that's an optimistic conclusion. Getting some people to be safer motivates other people to be safe. I should let us take a break now. Can we break for like 10? I know, I'm sorry, I went over. But break for 10 minutes and then at 12:09, we'll hear from Zach on regulating transformative tech.
Our fearless leader has left us for the moment because he's preparing the slides for this afternoon. So we're going to briefly talk about AI governance, regulating transformative tech, and specifically, this presentation is basically all about this one Asimoglu and Lensman paper, which is titled Regulating Transformative Technologies. The basic idea is, transformative technology, which they're going to apply to AI, is one that offers the prospect of increasing productivity growth across the economy while presenting potentially irreversible risks, and we learn about those risks over time. And we can think of these as existential risks. That's democracy, unemployment risks, cybersecurity risks. The way risks are going to be modeled is that it's just like a scalar that hurts your consumption index. So existential risk doesn't actually really fit into the schema because there's no probability that you're just wiped out completely. But maybe semi-existential risks or something. And the question the paper is seeking to answer is just how should we adopt and regulate such a technology? And it provides reasons for thinking adoption should be gradual over time, that regulating adoption may be beneficial, and faster productivity growth of the new technology may lead to slower optimal adoption. And then at the very end, there's going to be one slide where I talk about these two other papers that are on similar topics. I should say, and I'll talk more about this, in a way, this is a weaker definition of transformative technologies than we've been working with maybe in some of the other models, both because there's no explicit existential risk, there's no chance you're just going to die completely, and the good growth scenarios they're considering are more like, a 2 percentage point, 3 percentage point boost in GDP growth, not a 30 percentage point. I think the model has some implications for thinking about the 30 percentage point case, but it can't really be directly applied to that case. So you might think this is more offering us a framework for thinking about intermediate scenarios. So in the model, there's a continuum of sectors that produce final output. In each sector, you can either use an old technology, O, or a new technology, N. The level of aggregate quality of the old technology is QO, of the new one is QN, but then there might be some sector-specific comparative advantage of the new technology, Q alpha I. And then the X just tells you which technology you've chosen to adopt in that sector. And that's a binary decision, so it can't be like partially chosen. You're either using the new tech or you're not. And then so final output is just going to be a perfect substitutes combination of these individual outputs in all the sectors. And there's going to be different growth rates of the aggregate quality of the new tech and the old tech, with the new tech, which we can think of as AI, growing faster. The way disaster risk works here is there's some prior probability that like a disaster exists in this new technology. Conditional on a disaster existing, it's going to be exponentially distributed with a hazard rate lambda. So our posterior belief in the likelihood that disaster could occur at all, like that the disaster risk exists, is going to evolve like this. And the important implication there is you learn with time regardless of adoption. So it's just always the case that you come in with a prior, if you observe no disaster, you now have a lower belief in the chance that there's going to be a disaster from this technology. And conditional on the disaster, the higher your belief in the hazard of that disaster, the more you're going to update towards there being no disaster in the next period when no disaster risk whatsoever if you don't observe a disaster in a given period. And the way the damages work is that if a disaster occurs, any sector which is using the new technology suffers a flow damage that's rising in the aggregate capabilities or quality of that new technology, and then a sector-specific delta I. And with some probability eta, a sector using N cannot switch back after the disaster. And so the way that works is like, when the disaster hits, all these different sectors have their etas and are going to have some chance that instead of suffering that damage, they can just switch back to the old technology. But some sectors aren't going to be able to do that, and then they're going to suffer the damage. We assume the delta is uniform over some distribution of deltas, and then so overall damages is going to be indexed by the sectors that are using the new technology, because this is either 1 or 0, times the aggregate quality. And yeah, the key assumption here is that damages are proportional to the technology level. And so then we're going to start with the social planner problem and then get into the equilibrium that's decentralized. In the social planner problem, they're just maximizing the expected present discounted value of utility, where this is like good output and these are bad damages.
So what about the setup makes it applicable to 2% growth speed up and not to like a 30% growth speed up?
So it's actually this assumption right here. So the social planner is risk neutral, meaning that you need the growth rate of new technology to be less than your discount rate for the problem to be well defined. And then it's not that you couldn't set the discount rate super high and then consider 30% growth scenarios, but like we don't normally set the discount rate to be consistent with being greater than 30% growth. So I think they don't have this in the model, and I haven't like worked this out fully. So I started, trying to ask ChatGPT some questions about it and trying to work it out. But I think if you had risk aversion and you still had normal levels of rho, you'd get broadly qualitatively similar results and can consider much higher values of GN without like unrealistically calibrating rho, but that's not there in the model right now. And so this social planner problem can be cast in recursive formation, where we think about the value of the pre-disaster state and the value of the post-disaster state. So I don't know if people are really familiar with like, value function, Hamilton, Jacobi-Bellman equations that we use in macro. If you're not, I think these are still somewhat intuitive. So this is saying that the value of the pre-disaster state depends on the probability of a disaster and the Q, which is indexing both technology levels. And that value is just the output you get today in that state, plus the probability you enter a disaster state and move to the post-disaster value minus the non-disaster value, plus how that value evolves over time. And then the post-disaster welfare is just given by your output net of your damages plus the evolution of it over time. And the X bar equal to 1 indicates that in a given sector, you're irreversibly stuck on the new technology. To simplify things, we're going to assume that the comparative advantage in tech of the new tech in a given sector is less than the social damages of that tech. So anytime you can switch upon realization of the disaster back to the old technology, you would like to, because this damages are going to be greater than the relative benefits of remaining with the new tech. But some sectors are going to be irreversible, so they're not going to be able to switch back. And then we're going to now derive the rule for when to adopt this new technology in a given sector. So you start from the post-disaster value, you integrate it, and there's a proof if this step doesn't make sense, but we're not going to go through it. So this is the post-disaster value, the present discounted value of it. Then we can rewrite things using the fact that both old technology and new technology are going to grow at their respective growth rates, and that this is output in a specific sector, conditional on these X's where the bars, again, are indicating whether or not it's irreversible. And so then just plugging all of these in to this, and then using the fact that if it's growing at rate GO and you're discounting at rate rho, the present discounted value is the initial level over rho minus G naught or over rho minus Gn, if that makes sense. So this is basically when you're in the post-disaster state, you get this output from the sectors that are using the old technology, and you get this output from the sectors that are using the new technology, but this term's going to be negative because that comparative extra output you get is going to be less than the damages from the delta. And then if you take the conditional expectation over whether or not you're irreversibly stuck, you just replace these X bars with whether you've chosen to use the technology times the probability that you can reverse that choice or not. And then we go from here to figuring out. So yeah, from here, we can think about the pre-disaster adoption decision, choosing to adopt. So going from 0 to 1 on X yields the flow gain of the extra productivity minus the productivity of the old technology. But it also changes your expected post-disaster value by just the terms that are being multiplied by X in that period, which is just this. Yeah.
So the disaster probability does not depend in any way in your behavior.
Correct. It's just exogenous. Yeah, so I agree. I think there's like lots of.
Actually, I didn't vote on it, but I didn't.
What?
I didn't have the face to do it, but I don't know if everyone would see my thing.
Yeah, his face was very skeptical about that assumption. So yeah, this is the change in expected post-disaster value from giving to adopt in a given sector. And then we're going to choose to adopt if the benefits plus the costs, where I said plus the cost, I guess it's like this term is negative because this term is going to be negative, are positive. But you're adjusting for the probability that you're going to be in that state, which is your prior belief times the actual hazard rate that you're going to realize it. Then using this rule, we can realize that there's going to be an adoption threshold. So there's going to be some level of delta, which we're going to denote L, where for all delta i's less than L, you choose to adopt the technology at a given point in time. This is indexed like L's. I don't have the TX indexes right now, but it will be indexed by time. And if we denote little q to be the log quality gap between the new technology and the old technology, and assume that the comparative advantages and the irreversibility probabilities are constant across sectors, which is an important simplifying assumption, and they have in the appendix when you relax that, but it doesn't change the qualitative conclusions much. Then there's going to be some damage threshold where it's optimal to adopt if you have delta below L. And so if you just work out the math here, plugging in L for delta, rewriting the Q in terms of QO times the log quality gap, and then do the algebra, which I'm not going to go through these steps unless people are curious, you get to this condition, which we're not isolating L, but it's very easy to isolate L by just multiplying and adding the alpha to get what that threshold is at which we adopt. And I think yeah.
I'm kind of curious about one thing. So the whole thing is about
damage happening on the sectors that were like the technology was introduced. So like, in what way should I be thinking of like, so what would be the example of that? Would be like something like maybe I use LLMs to solve a problem for me, but there's something weird and silly, it's like Mecha Hitler, Grok and whatever, and now you have perpetual damage. Yeah.
That's kind of like the idea, right? Like
Yeah.
you're
Yeah.
relying on something and then suddenly it turns into unreliable.
Yeah.
And it gives you a damage.
Yeah.
But,
I agree. It's a bit strange because you might think that we shouldn't think the damages only apply to the sectors that have adopted. Like you might think the damages should just be across the entire economy.
Go with that as long as it's like not the only possible damage that AI could do. Right?
Yeah.
Like, I don't know, like you could think, well, maybe you want like automated agriculture and suddenly they made a very stupid choice and they destroy a unbelievable amount of land because they used like, I don't know, like cherry coke to water the plants.
Yeah. No, so I think there's lots of types of damages you could think of that fit in this framework. I agree. There's other damages that don't fit within it. I think, I think that's basically what I have to say about it. Was there another question? And then to get the comparative statics of this adoption threshold L, we can plug in the way the quality gap is going to evolve over time, which is that Q of t is equal to, sorry, this should just say Q of naught plus, there shouldn't be an equals in between there, plus the growth rates times time. And if we take that derivative with respect to the growth rate of the new technology, we get this expression. Again, there's a proof if you're, want to do that out yourself. But what's important to recognize is this derivative is going to be positive if and only if this, and then you like add that over and divide the mu of t lambda eta and rearrange. So the derivative is positive if and only if this condition holds. The derivative being positive would mean that the higher the growth rate of the new technology, the higher is your adoption threshold. So you're more willing to adopt when the technology is growing faster. But what we see is that the limit of this left-hand side as t goes to infinity is 0, because you're going to have this e to the negative infinity time term, which means that there must be some time t bar before infinity where that derivative becomes negative at all points t greater than t bar. And if the derivative has become negative at that point, that means the derivative of the adoption threshold with respect to time is also negative at that point. And then from the implicit function theorem, if both of those derivatives are negative, t bar is also itself decreasing in Gn. So there's two interesting implications there. One is that you have this stretch of time where the adoption threshold is the stretch of time beyond t bar, where the adoption threshold is decreasing in the growth rate of the new technology. So the more potential benefits it could give you, actually the slower you want to adopt it. And the faster the growth rate of the new technology, the sooner is that time that it's going to start decreasing in the speed of the growth rate of the new technology. Oh yeah, and then this is just that in words. But you can think of it as there being there's two offsetting effects. So there's the quality gap effect, which is just that the higher is Gn, the higher the relative benefits of using the new technology to the old technology. But then there's this precautionary effect that comes from the fact that the higher is Gn, the larger are going to be the damages if a disaster occurs. And at short horizons, the quality gap effect is going to dominate, but at longer horizons, this precautionary effect is going to dominate. And I think if there's like one key, there's interesting results to come about how should we regulate in these circumstances. But I think to me, the most interesting result of the paper is just this fact that the adoption threshold can be tighter when the growth rate of the technology is faster under these assumptions. Yeah.
You motivate the no switching back some industries assumption. Remember, I'm trying to think of countless examples of this.
Yeah, I mean, I think no switching back is extreme. You might just think there's some distribution of like adjustment costs of how easy it is to switch back. Like you've rearranged you've done all the J curve rearranging of your production processes to using the new technology. It's really costly to switch back. I think if it was like a continuum of costs, the qualitative insights would be pretty similar, but yeah.
QM also like keeps growing, right?
Mhm.
So in some ways, you actually think that there is a damage, but then you're kind of like the QM is already growing again versus the Q0, right? Or am I wrong about that? Thinking those terms.
Everything you said is right. I'm just not sure.
In those story, the model strength damages. The damage is permanent in the sense of my comparative advantage, but in the sense of like adoption decision, might still be justified to actually use the new technology at one point. Right? I don't know.
I mean, so conditional on being in the disaster state, any sector that is using the new technology is worse off.
Oh, it's always
Because of the assumption that
for some reason on the
because of this assumption that the alpha is less than the delta.
Oh, I see. Those, yeah.
So like, and because you know the benefits are alpha QN, the damages are delta QN. So as QN is growing, both of them scale proportionally, and because of this assumption, you'd always, if you're in the disaster state, always rather not be using the new technology.
Yeah, worse.
Yeah, I mean, like they're growing at the same rate, but no, QN and Q0 are not. I'm saying alpha I QN, which is the benefits of the new technology, and delta I QN, which are the costs, are growing at the same rate. But you're right that if, yeah, versus Q0. So I don't have this result on the slides, but like in the paper, in the same proposition that shows these comparative statics, they also point out that the comparative static with respect to the growth of the old technology is also like you have a higher adoption threshold. So the faster the old technology grows, the more reluctant you are to adopt the new technology. And that, I guess you can't just like immediately see it, but if you just took this derivative with respect to the growth rate of the old technology, you could figure that out.
And let's say the regret also like increases as growth of AI increases. Like,
yeah, I mean that's like the quality gap effect. And then to give a visual of this, this is for, so I believe like this is the gap in growth rates. So in one case, the new technology is growing 2.6 percentage points faster than the old. In the other case, it's growing 3.8 percentage points faster. And what you see is you have this in the larger difference regime, you adopt faster at first, but then there's this T-bar at which you start adopting slower. And adoption is very gradual. So X here is the share of sectors which have adopted. So it's not the damage threshold, but it's the share that have adopted. And that's kind of the key, one of the key interesting results. And so this is all from the social planner's perspective. Then the way we're going to think about the equilibrium is that firms only internalize private damages, gamma I, less than or equal to delta I. So it's, but it's still the case that the private damages exceed the tech's comparative advantage. So it's, even still, the firm doesn't fully internalize the damages that are being done to their sector, but they would also rather switch to the old technology conditional on being in the disaster state. And all the like equations and results from the previous section basically go through exactly in terms of the private firm's adoption conditions, just replacing the deltas with the gammas. So, you know, this was our same adoption threshold, just we had delta there, now we have gamma. And yeah.
I'm a bit lost.
So there was like a continuum of firms or sectors?
Sectors, but
And then each sector is like made up of a continuum of firms? Or...
yeah, I mean, so they don't actually explicitly say that, but I think that's like it's more like there's a representative firm in each sector that's just internalizing only some of the costs. It's a little weird because
it feels like a reduced farm, and then but like if it didn't take it as a reduced farm, it seems like self-defeating in some sense. It's like, oh, the firm gets all the profits from the sector and yet doesn't internalize all of this. But I guess it probably makes sense if you think of it as an aggregation.
yeah, I think that's fair. I agree. I was getting a little confused. Like I was getting confused about this when I was reading it, and I didn't fully resolve my confusion. But I think it makes sense to think like the sectoral output which can be consumed, there's greater proportional damages to that than like what the firm itself loses in terms of its profits. And that's basically what's happening. Like, because you might think that I think the way they're thinking about it in like the social media case or something is like, you're indexing the fact that maybe you're like getting your brain rotted, and that is showing up in the sector output damage function delta, but like the firm isn't incurring all those costs themselves because people are still using it, but the firm's still incurring some costs. I don't know. May or may not be plausible. And so then if this is the case, the equilibrium is typically going to be inefficient. So if gamma and delta are negatively affiliated, meaning like the order of the high delta sectors is opposite of the high gamma sectors across sectors, then the order of adoption by sector is going to be reversed versus what the planner would want. And that's going to be inefficient. Even in the case where they're positively affiliated, so gamma is a strictly increasing function of delta, we're going to have this new equilibrium damage threshold that depends on the shape of this positively increasing function. And so like this is the social planner's damage threshold. This is going to be the private sector's damage threshold. Because the gammas are less than the deltas, this equilibrium damage threshold is going to be greater than what the social planner would choose. And if this derivative is less than 1, the equilibrium damage threshold is going to increase more quickly than the social damage threshold. And that gives us too rapid adoption in equilibrium. And the way I chose to set up this presentation is that for those earlier results, I went through the math like a bit more. The remaining results we're not going to, partially because of time, though maybe we'll actually finish early, but the math's in the paper. And you can see this in this figure. So the dashed lines are in the decentralized equilibrium, while the thick lines are the social planner's choices. And you see that the adoption is more rapid in the decentralized equilibrium in both cases relative to what's optimal. So then what should we do as a regulator about this? To fully implement the planner's preferred outcome, you would have to lever a sector-specific use tax or adoption tax, and they show that this is the form that the tax would take to implement the optimum. And it's just given by the expected private discounted value of social versus private damages, because the delta minus gamma is the gap in social versus minus private damages, but you have to adjust for the probability of the disaster occurring and irreversibility, and discount by the flow benefits of the new technology. But that also scales, or you're discounting by the way the damages scale over time.
Previous, like in the gamma is smaller than delta. Like why there would be like a struggle to internalize this? Is it you just said externalities or whatever?
Yeah, it was kind of something like the social media example I gave.
I'm making a comment on Slack that relates to that.
Okay. I can't wait to see later. And so this sector-specific tax is going to be larger when the probability of irreversibility is higher, or when the gap between social and private damage is higher. It's going to evolve over time like this, which means that it is going to go to 0 as t goes to infinity if the hazard rate of the disaster is greater than the growth rate of the new technology, because you end up learning so much that no longer do you care about taxing adoption. However, we might think that doing a sector-specific tax is very, like, you need a fine instrument to do that. We can't do that in reality, in which case we would be restricted to sector-independent taxes. And so you can implement the optimum with sector-independent taxes if and only if the gamma i's are strictly positively increasing and the delta i's. And this is the form that tax would take, which again is about the social planner's damage threshold compared to the private sector's damage threshold. But if the gammas are not strictly positively increasing in the deltas, the equilibrium is going to remain inefficient. They then introduced this complementary tool called regulatory sandboxes. And the way this works is you choose some threshold delta and some threshold t, and you have it so that any sector where their deltas are less than this delta threshold can choose to adopt, but any sector which the delta is above cannot adopt until some time t, which is your chosen threshold. And then again, I'm not going to show you where this result comes from, but they show that combining regulatory sandbox and sector independent taxes, not of this form, because this is the form that's optimal when you have the positively increasing, but when you're now in the case where you have not strictly a positive relationship, then combining regulatory sandboxes and sector independent taxes is going to be better than either policy alone. With the idea that the sector independent taxes helps you delay adoption for sectors with different private damages, while the regulatory sandbox tool allows you to alter the order of adoption and specifically focus on preventing the high social damage sectors from adopting. But it should make sense that the sector independent tax is mainly affecting people relative to the private damages they're internalizing, while the regulatory sandbox is just looking at the social damages directly. And combining the tools is going to work better. So I think in terms of takeaways, at a high level, if we're going to learn about the risks over time, and that there's some chance of irreversibility of those risks, then it seems like a pretty natural point that you can make a case for gradual adoption being optimal. If risks scale with capabilities, and again, you have this potential irreversibility, I think the most interesting point that I take away from this paper is that this adoption rate can be decreasing in the growth rate of capabilities. And then if firms don't internalize the social damages, there's regulatory solutions that can be helpful. In terms of limitations, which you've kind of talked about, I think one important one is the disaster arrival rate and learning rate are independent of adoption. You might think we only really learn about whether a disaster is going to happen or not by adopting, not just over time, no matter what happens. There's some informational things where it's can we really discriminate well across different sectors, specific damages, which kind of gets at the question of maybe the damages are more just aggregate in nature. The point about risk neutrality earlier, I think, you would imagine that risk aversion might make the adoption even more gradual, but it's just currently the assumption the paper's working with. Therefore, we're not really looking at explosive growth scenarios or growth uncertainty, but I don't think necessarily adding these things in would push the paper in the direction of more aggressive adoption. I think the results could kind of go either way. Any more questions about that paper before I have one slide on 2 other papers? Cool. So there's this Gans paper from 2024. In his paper, there's two different technology paths, and learning about the harms of those technologies comes from adopting. So it's not the case that you just learn over time no matter what. The development of each technology, rather than just growing at some exogenous rate, like in what we just saw, is going to depend on chosen research investment. Harms are going to scale with adoption rather than with capabilities, and there is going to be reversibility of technological decisions. There's more, assumptions, but the basic results are now it may be optimal to double down on a technology because harms are scaling with adoption rather than capabilities. You can get capabilities to outgrow the costs by doubling down on your research in that sector. And in this environment, rather than kind of like ex ante regulation, ex post regulation is going to work better, since it internalizes the prospect of harm when there is uncertainty. With the idea being that the researchers who are choosing to invest know that there might be ex post liable and internalize this fact in their investments. And then there's this Ko and Sangwanmu paper, different environment. So private researcher who's more risk-seeking than society develops a technology which could be harmful or beneficial, and like the actual state of whether it is a binary outcome, unlike what we just saw where there's both benefits and costs. The researchers privately learning about this information as they develop the technology. And what they're interested in is kind of regulatory mechanisms that ensure against the worst case. So specifically, regulatory mechanisms which deliver worst case guarantees across all learning processes the agent might face, or more stringently, across all learning processes and agent preferences. And their result is that regulatory sandboxes, which don't have the exact precise meaning they did in the previous paper, but have the same concept where it's like you're able to do it as much as you want up to a point, and then you're cut off beyond that point. In this case, where you have zero marginal tax on R&D into this new technology up to a limit, and then like infinite tax after that limit, satisfy these robustness properties and are dominant among robust mechanisms. But the robustness is doing a lot there because it's like the theory sense of robust where it's in the worst case scenarios, which is different from what we've looked at in this previous paper where there's no notion of like min-maxing, you're just looking at optimal. And that brings us to 12:45. Thank you guys.